Okay, today we're going to look at free body diagrams, what they are, and how to draw them. So before we talk about free body diagrams, we need to talk about types of forces. There are contact forces. Those are forces that happen when two objects actually have to be in contact with each other, and they include frictional, tension force, normal force, air resistance, applied, and spring force, which we'll all talk about today. Action at a distance forces are where two things interact, but they don't have to touch. And that is gravity, electrical force, and magnetic force. Now those are things that we've talked about gravity some, but electrical and magnetic force are things that we'll talk about later. But what we're going to deal with today with free body diagrams is all the contact forces, and then of course gravity will come into play. So when we talk about force, the units are in newtons. 1 Newton is the same as 1 kilogram times meter per second squared. Now, this kind of goes into a Newton's second law, where force is equal to mass, which is in kilograms, times acceleration, which is meters per second squared. So F equals ma is how we get the term Newton. Newton, from Newton's laws, is mass times acceleration, 1 kilogram times meter per second squared. So force is a vector. And we kind of looked at this situation in the previous video where you had a physics book sitting on a table. Gravity's pulling it down, let's say, with a force of 20 newtons. So its weight is 20 newtons. But the object's not accelerating, so therefore our forces are balanced, which means the table pushes upwards with a equal but opposite force, Newton's third law. So 20 newtons up. So this is what we see with the book. With this book, it's going to the right. It's going to the right. We're not touching it. We're sliding it to the right. The forces that are acting on it are the same two from before. Gravity and the table pushing up are balanced because we're not accelerating in the vertical. But in the horizontal, we have an unbalanced force, and that's because as the book travels, friction's pushing it 5 newtons to the left. So the book's going to slow down. This unbalanced force leads to an acceleration, which is the book slowing down. But force is a vector, and we use the arrows to designate that. So, here are the types of forces. The first type of force is called an applied force. And that's any time an object or a person applies a force to the object itself. So you could be pushing a chair across the floor. You could be rolling a ball across the floor. Anything where you're constantly touching it, okay, to make it go. So that's an applied force. And force app is how we see that designated. Gravity force. Now, force of gravity is known as weight, okay? And that's when two objects of mass form an attractive force. And so, by definition, this is the weight, okay? So when we talk about gravity force, Fg, we're also talking about weight. Now, all objects upon Earth experience a force of gravity that is directed downward. We've talked about this before. The force of gravity on Earth is always equal to the weight of the object as found by this equation. Force of gravity equals mass times g, where g is 9.8 and mass is in kilograms. Okay, so g is 9.8 newtons and mass is in kilograms. Okay, g is 9.8 meters per second squared. Sorry, it should be meters per second squared. And mass is in kilograms. And then that's how we can find the weight of any object. Mass times g. Important, write down this formula. Normal force. The normal force is the support force of an object that is in contact with another object that is not moving. So, like for our book on the table, you got gravity pulling it downward. But it's not falling downward because the table's pushing right back up with an equal and opposite force. That is our N, normal force. Force normal is what goes against that, okay? And a lot of times normal force will go against gravity of a stationary object. Then you got frictional force. Again, designated. You can write it big F, little f. You can write out fric, I don't care, as long as you know what it is. But a frictional force is the force exerted on a surface as the object moves across it or makes an effort to move across it. So there has to be two objects in contact where one's moving across the other. You can have sliding or static, and we'll talk about those more in detail when we talk about friction. But sliding friction is when the object's moving, right? And then static friction is when the object is not moving or stationary. Okay? Friction almost always opposes the motion. Now, it's not always, but almost always. And the force of friction has a formula. Again, we'll talk about this more. It has a constant called mu, the coefficient of friction, and it's multiplied by the normal force. But frictional force, another force we're going to have to look at. Air resistance force, force of air. Usually you see it written like that. And that's because air resistance force depends on objects as they travel through the air. And there's almost always air resistance. But the big thing about it is this force is usually neglected due to its negligible magnitude, which means it really doesn't affect things that much. Plus, mathematically, it is difficult to predict what it's going to do. So air resistance exists, but normally you're told to ignore it. Force of tension, probably the force that we'll spend a lot of time with. Force T, force of tension, is the force that is transmitted through the string, rope, cable, wire, anything that is like a string. Okay, not a spring, because that's a different force we'll get to, but it could be a string, rope, cable, wire. Now, here's the thing about tension force. Okay, two things actually. It needs to be pulled tight. So let's say you have an object hanging from a string, right? That string's tight. But the tension is directed along the entire length of the wire and pulls equally on the objects in the opposite ends of the wire. Okay? So if this object is standing like this, standing still, it's going to be, the force of tension is going to be the same as the weight. All right? But force of tension is over the entire wire, not just a part of it. The last thing's the spring force, and that's any time instead of a wire we have something attached to a spring, let's say. Okay? So if this compresses the spring, then that's a force that makes that happen. And this is a special thing we'll talk about with harmonic motion. Okay? And it's called Hooke's law. But really we're just trying to identify spring force if it exists. All right? And that's another force we need to think about. So, free body diagram is essentially a box where we identify all the different forces acting on an object. In this case, we have a normal force, a gravitational force, an applied force, and a frictional force that's acting on this object. We look at the length of the arrows. The length of the arrows tells us the magnitude, so if one is longer than the other, we're going to have an unbalanced force. If they're similar in length, the forces are balanced. So, for example, we have a book at rest on the tabletop. So you have, in this case, you have a tabletop, you have your book, you have gravity pulling it down, but since it's at rest, my forces are balanced, therefore my normal force is just as great as my gravitational force. Here's a gymnast holding onto a bar suspended motionless in midair. The bar is supported by two ropes that attach to the ceiling. So what's going on here is that we have the gymnast, gravity's pulling them downward, but we have two ropes holding up the gymnast. Since the object is stationary, our forces are balanced, which means gravity is equal to the two tensions. And again, we want this arrow and this arrow together to be equal to the length of this arrow, just so we can show that this object is stationary or not moving, and forces are balanced. An egg is free falling from a nest in a tree. Neglect air resistance, and you'll see this a lot. So if an object's falling, the only thing acting on it is gravity. There's nothing else. We're not pushing it. We're not throwing it. Even if we throw it, once it leaves our hand, we're not applying a force to it. So when something's in free fall, the only thing acting on it is gravity. And remember the force of gravity? If I wanted to find it, I take mass times g. And on Earth, that would be 9.8. So a flying squirrel is gliding, no wing flaps, from a tree to the ground at constant velocity. Consider air resistance. Okay, so the key here is constant velocity, tree to the ground, so we're going downward, right? But if it's constant velocity, our forces are balanced. We're considering air resistance. So if something's falling down, the air is pushing up. So here's our object. We got gravity down, air up. But again, our arrows are the same length because we're at a constant velocity. Okay, a rightward force is applied to a book in order to move it across the desk with a rightward acceleration. Consider frictional forces, neglect air resistance. Okay, so forces that are acting. It's across a desk, right? And it's going to the right. Okay, so we have friction. Friction always opposes motion, so friction goes back. Applied force is going to the right. We have gravity pulling it down, but since it's on a flat surface, we have normal force pushing up. These two arrows are the same length. Though it's hard to see, and you may want to exaggerate this when you draw them yourself, if it's moving with a rightward acceleration, okay, that means the unbalanced force is going to be to the right. The greater force is going to be in the direction of the acceleration. So this arrow will definitely be longer than this one. And in the diagram, it's kind of long, but you can make it longer if you want. Applied force greater than frictional force. A rightward force is applied to a book in order to move it across the desk at constant velocity. Consider frictional forces, neglect air resistance, so there's no air resistance. We have friction. So we're applying a force, and we have friction, okay? Our normal force and gravity are equal because we're going across a desk, just like we previously said. But it's moving at a constant velocity, okay? Which means forces are balanced, which means frictional force and applied force also are equal. And what we would see is them be equal, because we're moving at a constant velocity. A student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. So we have this suspended backpack. Gravity's pulling it down, okay? But what's holding it up? Well, the tension on the backpack. And since the object is motionless, it's not accelerating in any way. Our tension force and gravity force are equal, so our arrows are the same length. A skydiver descending with a constant velocity. Now we're going to consider air resistance. If somebody is falling with a constant velocity, obviously gravity's pulling them down. But we have to have something pushing it up because we have a constant velocity, and that turns out to be our air resistance. Now, we'll probably talk about this later, but when we have air resistance and gravity equal, this velocity that we're at, right, we call that the terminal velocity, where air resistance and gravity are equal to each other. And that constant velocity we get to is called our terminal velocity. A force is applied to the right to drag a sled across a loosely packed snow with a rightward acceleration. Neglect air resistance, so there's no air. So once again, we have a rightward acceleration, so our applied force is greater than our frictional force. But normal force and gravity are going to be equal because we're dragging it across, right? So these two will be equal because we're accelerating rightward, not up or down. And applied force, since we're speeding up, applied force is going to be greater than frictional force. Football's moving upwards toward its peak after being booted by the punter. Neglect air resistance. Once it leaves the foot, nothing else is acting on it but gravity. That is free fall. Therefore, the only thing acting on our football is gravity, and therefore we have an arrow pulling it down. A car is coasting to the right and slowing down. Neglect air resistance. If it's coasting to the right and slowing down, that means we're not applying a force, so there's no applied force here, okay? But friction's pushing us backward because we're moving to the right, but we're slowing down. Friction's opposing our motion. Normal force and gravity are equal because our car is going to be on a flat surface, or we're going to assume as such. But our friction's the only force slowing us down, therefore that's an unbalanced force. The length of our arrow for friction does not matter as long as there's an arrow because we have no applied force. Now, before I shut her down, the one thing I want you to think about when you draw your own free body diagrams. One, always consider the fact that gravity exists, okay? I cannot make that stop. If gravity exists. Two, make sure you think about all the different things occurring. If there's air resistance, make sure you account for it. But if it says neglect it, don't worry about it. And three, when we're in free fall, the only thing acting on us is gravity. Don't try to find forces that aren't there. If it's not in contact, it's not a force. All right, I'll repeat that again. If it's not in contact, it's not a force. We can't apply a force to something once we're not touching it. As you work on your free body diagrams, ask questions, and I think you'll be fine.